Oke, sudah live di YouTube ya. Ini hostnya saya operkan ke Pak Jati atau ke Mbak Dian?
Mas, saya di departemen pakai laptop. Saya khawatir saya baru masalah. Atau jadiin co-host aja deh.
Oke, kalau gitu saya tetap hostnya saya aja berarti ya.
Enaknya
ya,
sih ada host, ada co-hostnya 2 gitu ya biar.
Oke, berarti hostnya di saya, co-hostnya Mbak Dian sama Pak Jati gitu ya.
Boleh.
Oke.
Ya deh.
Oke, sudah.
Sudah ya Mas. Oke, makasih Mas Adam. Nah, ini tinggal Prof
Oke, ya. Cuman ini di-off-kan ya, soundnya karena pakai mic kita. Jadi soundnya dimatikan, saya dimatikan juga aja. Nah.
Tadi udah masuk UI sih katanya.
Ya, orang-orang Jepang, Korea itu tampil-tampil saya juga punya sesuatu
ini membantu betul Korea. Jadi satu hari di sini langsung Bandung, nanti ada Bandung selesai sore langsung ke Surabaya. Di Surabaya selesai sehari langsung balik lagi ke Jakarta naik pesawat.
karena kaget bisa. Tapi kalau kemarin kan sempat kontak saya sebelum ini nggak urusannya nggak coba karena saya nggak bisa akses. Yo lagi main pengen juga sekarang ada apa juga. Iya, sama kita udah yang baterai. Karena dia tahu saya baterai karena ada kayaknya dana yang dia cuma kayaknya nggak iya. Tidak fanatik banget. Dan sekarang sudah ada waktu awal kan saya mau cuma karena saya yang baterai sudah dilakukan. Ya mungkin belum tertarik masuk ke sana. Sekarang trennya karena si Alan True juga udah main baterai. Waktu itu kan dari sini sadar lagi baca orang baterai mereka.
Jadi yang lain itu kenalan.
Baca waktu dari sini saya bisa
Iya.
hanya mereka Alan juga putar tadinya yang Muon segala
Baik, kita akan mulai saja ya. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera semua. Good morning, dear students, colleagues, and our invitation speaker from Rikeng, Professor Isa Watanabe. Good morning and welcome again in Physics Department, Universitas Indonesia. I think more than 2 years after the COVID pandemic, Professor Watanabe now come again in this room. Usually, Professor Watanabe come here every 1 year, to give new information about the Muon facility in Japan, in ISIS, UK, and in other places. But due to the COVID pandemic, so now he just come to Indonesia again. And here I want to introduce you Dr. Jati Handoko as our physics head of the physics department. And there are some of our students here, and some of the our colleagues here. Now, we would like to give our high appreciation to Professor Isa Watanabe. We know that he just arrived from the Canada, from Canada, and then he come here, and after this, in the afternoon, he will go to the Unpad Bandung, to have a meeting with Professor Rizdiana and his colleagues in Unpad. And the next day, he will move to the ITS Surabaya. And after from the ITS, he will return to Japan again. Is it right? So it is long journey from Tokyo, yeah, to Jakarta, Bandung, and also to Surabaya. Yeah. And last night, yeah, he just arrived at in the middle of night, about 0005. But since at the same time there are many flights, yeah, landed at the Soekarno-Hatta International Airport, so there is many queue in immigration and also in baggage claim and also, yeah, and so on. So he just arrived at the hotel about 2:45. Yeah. So yeah, I wish he have a good health since now in the morning he come here. Yeah. Okay. There's information about how hard Professor Watanabe come to here. So please, yeah, use this opportunity for you to give some information, and also maybe some of you want to go to the RICAN, yeah, you can ask to Professor Watanabe what kind of scheme you can use, yeah, to go there. So now I would like to invite Professor Watanabe to explain about the RICAN, yeah, what kind of what is the RICAN, what facility in the RICAN, and what kind of activity that is doing, yeah, in the RICAN. So Professor Watanabe, time is yours. Oh, before that, I want to Dr. Jati to give closing remarks. Yeah, yeah. Please.
Assalamualaikum warahmatullahi wabarakatuh. Salam sehat, salam sejahtera untuk kita semua. Good morning, Professor. Thank you very much for your coming in our department again. Hopefully today, in this beautiful morning, we can discuss and also maybe more intense collaboration among our institution. And hopefully some of you can go to Japan in this year or next year, hopefully. So again, thank you very much, Professor Watanabe, for your coming. And hopefully you still have good, healthy in this trip, very tough trip, I think. So by said Bismillahirrahmanirrahim, I open this discussion and hopefully we will have very nice result at the end of this meeting. Thank you and wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Jati. And now I will invite Professor Stawit. You can.
Great. So thank you so much for giving me this opportunity to talk about the something today. Since I have an hour, so then I'd like to a little bit speak speedy about RICAN and about my activities, research activities, and also introduction to the new project, which I'm now thinking to get a good funding to work with all of you. That is like international collaborations funding. Okay, so the first, better to introduce by myself and also what is RICAN. So here, this slide, already pointer gone. This slide is just like a report of the Sakura program, which is provided by JST, the Japan. So then what I'm not doing with these people is the JST provides money to invite the younger student researchers to Japan. to work with the Japanese researchers. So I've got 2 grants for this program. The one grant is with my old student. He is in Sulawesi now. And he's just bringing 7 students from Sulawesi to Japan in this Sunday, on this Sunday. I'm going to back to Japan by the same flight. Then they will spend 1 week with us in Japan. So this one is the same program, Sakura program, done with the UNPAD people. And she is Utami Vidya Iswari. She graduated from UI. So she is a 3rd student who worked with me and joined from the UI. First one, second one already has got the jobs and working in Indonesia, but she decided to leave, to stay in Riken. So she's now in just like a postdoc to me 1 year and applying the much more higher status. So she's now very keen to do the research in Japan based on the pyrochlor oxides. She's in Sendai, synthesizing the single crystal with one more new student from UNPAD. So 2 are now staying in Sendai. Sendai is a little bit north, around about 500 kilometers from Tokyo. So just I've got an email, asked for a message from the Utami-san. So she's now waiting for students to start to work today. So anyway, so I graduated from Hokkaido University a long time ago. So then they joined to Riken, the research institute that is in the Tokyo, near Tokyo here. So this one is the main campus of the Riken. So Riken is one of the 3 biggest national research institute for natural sciences. So there are 3 special research institutes in Japan: NIMS, ICE, and Riken. So Riken is one of them. Here is the main campus in the Wako city, which is very close to the Tokyo. If we walk around a couple of minutes, 5 minutes, we can come into Tokyo. And very easy to access to the center of Tokyo. And we are now staying in here. My students are also living in here. At this moment, I have 2 students from Indonesia. The one is from UI. The another one is from UNPAD. The one student from Thailand, Kasesa University. And another one is the University Science Malaysia, from Malaysia. So now I have 5 students at this moment. So then the next opportunity for young students will be open very soon after the summer. So then I'm trying to recruit the young student. So here is the main campus in the April season, the cherry blossom. Only 1 week, we can see this beautiful view in Riken. So Riken has many, not so many, branches in the world and also in Japan. So this is my branch in the UK. So I have been working in the UK more than 30 years already. So they are working on Muon science. So here is my basement in the UK, Rutherford Appleton Laboratory. So here we have the facility, the old facility. Then I'm in charge, the MIRSA, that is material science at the Riken Muon facility. So then I bring my students to here and study with my collaborators, and they can learn about what is MIRSA. Very, very rare technique, because there are at least only 200 researchers are working in the world. So this is very rare technique, but very strong and interesting techniques, and very famous in the world. Not so many people can do. We started the project from 1992, and also I joined. I'm here now. This is my first year to work on the Muon science. Here is me. So we constructed a facility, and then they continued to work with the British, the government and British groups. Then renewed the MOU, and then we are now coming into the new scheme, how we can continue our facility. And also mainly Japanese users are coming in, then worked with us, and then joining their science. Here is Diana. Here is now professor, big professor in UNPAD. He also worked with me. He used to be a postdoc to me. Then studied MIRSA for 3 years and came back. So this one is all the students, the Retono-san, ETS, Rita-san from ETS, but she's now the staff of the one private Japanese university, and she's also still working with me from Malaysia, and she's also ETS. So now she's a staff of the ETS. He's a Korean. So he's now the staff in the some Korean university. So then we have got many the collaborations, mainly domestic collaborations and also worldwide the collaborations. So if you join to our group, I'd like to ask to join to this kind of the worldwide the collaborations. So why the reason why I'm here now is just this Lisiana, Professor Lisiana. He used to be a postdoc to me, and through him we started to talk with researchers in Indonesia. Then just started, and we made an MOU in 2008 with ITB. This is a very fast starting point for me to discuss with Indonesian groups. Then renewed the MOU. This is a very memorial, the renewed MOU in Bali. So then this year, Professor Lisiana is planning to have the similar conference in November again, after the G20 meeting in Bali. He said, Nusadua, maybe tomorrow and also the after tomorrow, I discuss with him how we can organize this conference. And luckily, I've got some grant to support Japanese people to join to this conference. So maybe I will bring 10 to 15 the Japanese high class, the staff members and the researchers from Japan to this Bali conference in November. So then you can talk with others. So then you can find out the new opportunities or new directions in researches with the Japanese groups. Please think about. So these are just how we can work together. Here, Redo Ramadan, he's also from UI. She's now the staff of the private university of Japan. They are from Malaysia. And Tita, Letono, Fahmi, and Julia. They worked on Muon science with me and got the academic jobs in their hometown, in home countries. Interestingly, all of the Indonesian students, 100% of Indonesian students have got the academic jobs in Indonesia and Japan. Very, very good. This is just like an atmosphere to work with us. This one is a Bali conference, which I organized with Professor Lisiana. So this one is also the Professor Lisiana here. So then this one also the very memorial activity. So then I'm now coming back to this level, then to organize the conferences with the other friends in Indonesia, Malaysia, and Thailand. So this one is my record to have the seminars, talks in Indonesia. This is the UGM, UI, Buddhist here, young Buddhist here, also here. And Michael-san note, something around here. So this one, the Lombok, the conference, maybe some of you are there in here. And USM Malaysia, and Penang, Malaysia, and also we invited the British guy. He's also quite high level, the professor in the Queen Mary University, but enjoyed the dancing, Bali dancing like that. So then this one is the old picture, all my team member. They all are coming from, he's Ilwan. He's now in the Sulawesi. He's bringing 7 students there next week. Then we go to the Kobe to see the Fugaku. Fugaku is now the supercomputer system in Japan. Now is the speed in number 2, but other speed is still number 1. To see the Fugaku and also supercomputer systems in some universities. So that is the introduction of me. So then the next one is I introduce my research activity. That is Muon science. Muon science is a very, how can I say, rare technique by using the particle muons. Of course, muon cannot see by eye, and we cannot operate, but by using the physics and the particle physics knowledge, we can gather muons and introduce the materials and study electrical state. Even though we use the nuclear science technique and also particle science techniques, we can study the materials. That means the Muon is not for the particle science, but for material science. So my basement in the UK, like that. So then, these days in Japan, Muon, the name of Muon is becoming famous because Muon can penetrate and pass through the many materials. Then how we use the Muon is just like an X-ray detector. So for instance, there are many muons flying from the cosmic space, just from the top, from the space. Then we should see some muons, for instance, one particle muons per 1 second on your hand, still coming in. So we detect those muons and to see the inside of the Earth or volcano, and also pyramid. So this one is a volcano project, organized by University of Tokyo Group. So they bring the detectors. These are detectors. They brought detectors and set up like that. So then they're transparent. They see the inside of the volcano like that. So if the reason why is to predict when the volcano is burned. 2 days ago, there is a very famous big volcano in Japan, in Kyushu, Sakurajima Island, that was collapsed. So it was very big, the corruption. So then still everybody is now escaping from the volcano area. So how to predict when that is burned? So that is one of the motivation of this research. But of course, I don't work on this. The University Tokyo Group are working on this. And also the most famous one is the pyramid. Very this 2 years ago. So Nagoya University group just set up the muon detectors in the Khufu, King Khufu's pyramid, the largest pyramid in Egypt. So then they detected the cosmic muon, which is passing through the pyramid, and found like this. Okay? These are the Nagoya University's team member. They are setting the muon detectors like this. So then they found very interesting empty space here.
Pak, jadi
So this one
suaranya
is
mati,
the
Pak.
main corridor.
mati.
Here is the king's room. Here is the queen's room. But they
Sound is
found
off.
much more larger empty space just beyond the king's room. Unfortunately, no mummy was in the king's room. So then Egyptian researchers are very exciting because maybe this space could be a real king's room. So there could be a mummy of the king inside here. So then now they're measuring how large space we should see in here. So then we use accelerator, and also there are 4 muon facilities in the world. Here's PSI, Switzerland, and also Triumph, Canada, Vancouver, and JPAC in Japan. This one is my basement in the UK. So just I've been to here, 2 weeks ago, and to carry out my research for 10 days. I used to be here long time ago. So then, but never been to here more than 20 years. Then here is surrounded by the forest, but now this is not. The many mansions, the buildings are around the Triumph. So it was very impressive. So then Utami-san applied one proposal to Triumph. Maybe that will be accepted. If so, we will go to Triumph again at the end of this year or beginning of next year to carry out the MSR by using a directional refrigerator. So then the muons, there are so many muons. There are so many muons there, but we use a surface muon. If I talk about the details of the muon, it takes long time. So then I will skip. This one is like a slide for the lecture. So then in here, we see the accelerator here. So then we use a recurrent muon facility at here. So this accelerator is the strongest accelerator in the world. So then we can have the strongest muon beam at the recurrent muon facility at this institute. But recently, JPAC quality is now becoming better, but still the beam intensity at the Rutherford Appleton laboratory is much higher than JPAC. So I'm now starting to discuss with the JPAC people how we can accelerate the muon project in Japan. Maybe next 5-10 years, I will work on the JPAC much more to make this facility and much more better. So my activities, there are 2 types. I'm now working the experimental side and the computational side. Experimental side, the muon spin relaxation, and the computational side, the density functional theory calculation. So completely different. The experimental side, MUSR, we need a power, physical power. And DFT side, density functional theory side, we don't need the physical power, but we need the skills to do compute and calculations. So then we have two types of students. One is working on the MUSRs, another one is working on the DFT. So then I can gather. So then if you're interested in one of them, I'm very willing to talk and also accept the students. So MUSR is just like NMR. MUSR means it just you input a muon and see the dynamics and statics of the electrons inside the material. So image is just like a MRI. So, NMR, by using NMR, you can scan the body. That is with MRI. So MUSR is very similar. The principle is very similar. So muon has a spin, and we can see the resonance of the spin. The spin of the muon. So that's only. Then put in the muon, then see the resonance, then detect the signal, then discuss the electric state. The complete same with the NMR. But important point is the muon has a much more sensitive character, which is better than the nuclear. So then, for instance, the NMR, they cannot detect the 1 Gauss internal field, but MUSR can do. So that means we say the very sensitive, the magnetic probe, is a MUSR. So sometimes the muon is very, very sensitive, so better than NMR. And those NMR needs the NMR nuclei. However, muon doesn't need anything, just because we put the muon in from outside to the material, then we don't need anything. Just put in the muon into the material, then discuss the electric state. That is a strong advantage of the MUSR. So this one is a concept, how to detect. We put just on the muon counter in front and back side of the sample. Then the signal is detected, the counters, and we see these kind of signals that we discuss. Of course, due to time limitation, I don't explain how do we discuss this kind of the time spectrum. But if you're interested in, of course, I'm very willing to talk about in detail and explain about this. So then here is a spectrometer, real spectrometer, which is not so big, but the price is very expensive. For instance, the total cost of this one spectrometer is 10 billion rupees. 10 billion rupees. So these are from ETS, and they've got a job in ETS now with the Professor Darmintos, the place, and enjoyed 3 years, and they have some papers already, and graduated, safely graduated, then has got the job in ETS. Then on Friday, I will meet with them and discuss how we can do the new collaborations. So then this one is a lecture slide for MUSR. So then there are many, many details things there. If I talk about this, I need 2-3 hours. Then today I will skip. For instance, the one advantage to use muon is to study the superconducting state. Because I think you study the type 1, type 2 superconductors. So especially type 2 superconductors are very nice for the MUSR. For instance, in the case of type 2 superconductor, if you apply the magnetic field to the material in the superconducting state, the magnetic field is distributed like that. This is just like a textbook style. But in this case, interesting point is internal field is distributed, but muon can detect place by place. So that means all muons feed the different internal field. So then in this case, what's happened is the muon precesses around the magnetic field, but that field is different place by place. Then such kind of difference that we can detect from the damping ratio, the muon spin precession. Then from that, what we can discuss is the type of the Cooper pairing the state. So Dita, she's from ETS and now is a staff of the one university, Japanese university. she published this kind of the application 2-3 years ago on the basis based on the organic superconductor and discuss the new pairing state of the Cooper pair, new symmetry of the Cooper pair. So this kind of this one is a slide from, I got this slide from the data. So then the muon comes here and comes here, precess in the different frequencies, and we can see the difference in the muon spin precession frequency. This kind of frequency is easy to observe. This is background. So this is the normal state, and superconducting state, we can see the damping state, the muon spin precession. So this one we can analyze, then we can discuss the symmetry of the Cooper pair. That one is one of the strong point. For instance, this one is also typical high TC superconductor. In the superconducting cell, we can see the very strong damping of the muon spin precession. So then this temperature dependence we can analyze by using the existing theory. Then we can discuss a new type of the symmetry of the Cooper pair. So that is one point. So then next one is the examples. So this one is also high TC, but not superconducting state, but also studies the magnetic state. So also the magnetic state is a good target for the MSR. We can discuss the magnetic materials. And so this one is a low dimensional magnetic materials. This is also the quite good target. So this one was the collaboration with the ITB people. And this one is a fluctuating, the frustration system. Frustration is also a good target. Last month, I went to Paris to attend the largest conference for frustration, magnetic frustration in Paris. So then the Utami, she's got the oral talk. The oral talk has only 104 were selected as oral talk session, but Utami has got the 104. Then she had 15 minutes presentation in front of more than 200 researchers and appealed her success, the result. That was very nice. So then the Utami is still in Japan, but if you are interested in her experiences, please contact with her at any time. She is very willing to reply to you. So this one is also frustration, and discuss the multi-frustration like a spin lattice relaxation. This one is a pyrochrome system developed by Letono. Letono is in the ETS now. So this one is succeeded to the Utami. Then Utami is working on this pyrochrome, and now she's now trying to break the like a usual concept of the pyrochrome systems. And also this one is also interesting, like a zeolite. With Osaka University, the friend, the zeolite is also has a very weak magnetism, but because muon is very sensitive, so we can discuss a very weak magnetism. And high TC, this is my friend, Francis Platt. So she's very, very excellent researcher. Then she's got the Nature paper. Luckily, I'm a member of this letter. This one is also a spin liquid system. Spin liquid also interesting target. And 1D, the JAX communication, the 1D system, the many systems we can discuss by using muon. So then, because the magnetic materials, superconducting materials, and recently organic materials, this is also carbon nanoscience. That also possible. At this moment, one UE student is working on nanoscience. So she's been to Vancouver last week to attend the M-Squares, the international conference. That is the biggest and largest famous international conference for superconductors. So every day she sent like photos. I've been to here. But interestingly, there is no photo in the conference site, just on the sightseeing site. So anyway, so then at this moment, until now, I talked about the experimental procedure. So now how we can use MUSR more and more, and how to discuss deeper the character of the electric state. So that is, we need a computation, the performance and computation efforts. That is a little bit difficult, the system, because we have to calculate the electric state that is simply, not simply, just very difficult. Everybody said the different result because the computational techniques, there are many, many computer techniques and depends on the computation performance, machines and people and techniques. So which one is the real, result is very unclear. But the one clear point is better to use a very large machine, not like this. This kind of the PC. I've got this PC this year. This is very high quality PC. And like a memory, I have 32 gigabyte and 2 terabyte hard disk. And also CPU is the latest CPU provided from the Intel. But this kind of PC is still not yet good enough to discuss the real electric state. Then what we have to do is we have to know about electric state and also MESR. Then we have to understand Muon. Then we are now using the supercomputing system named Hokusai. This is a reckons the supercomputing system. This is being upgraded every year, every 5 years. So then the speed is not so bad, and also capacity and memory, and also bad. Maybe number 5 or 6 in Japan, among Japanese universities. Number 1 is the University of Tokyo. That one is the most expensive one, but speed is just nearly double compared to our Riken's facility. So then as long as we use just only double speed or half speed, but we can have the realistic and also reliable data by using Hokusai. But in order to use this, we have to understand the computational languages and programmings. And also I'm using the commercial based but high quality programming system named BASP. Then all the students from ETB, ITB, and also UNPAD, they developed how to use and how to do the calculations. So these are the results. And then the Redo Ramadan, he was also coming from UI, and he developed and completed. And 2 weeks ago, his paper was published in the physical level research. Physical level research still doesn't have the impact factor, but the quality of the research studies and papers, everyone said quite high level. So then if you're interested in, could you please visit physical level research this year and Redo Ramadan and my name, then you can hit. It takes about 2 years because there are many the batterings with the referees. So then in the beginning, I prepared only 4-page paper, but adding more data, then that became to be 12 papers, 12 pages, because the referees requested. This is very new, very original. So better to provide the detail, the result, to show how to do to general readers. So then as long as you can understand that paper, maybe you can repeat the same technique. So this one is a distribution of the mighty moment. Mighty moment, we usually say mighty moment just like an arrow, If you write the mighty moment, we make just like arrow, then we discuss in the classical view. However, in a quantum viewpoint, the mighty moment should be distributed. So this one is the result. Then we can draw up the distribution or the quantum distribution of the mighty moment, the spatially distributed. Spatially distributed means we have to count every component. So then every component means too many components, more than 10,000 or 20,000 components. Then everybody has to be calculated exactly. Then we need a high performance supercomputing system. Then we can do this kind of the calculation. So then by using this computational technique, we can analyze the Muon spin depreciation frequency. 例えば, for instance, okay, I show you the paper, Redo's paper, and Utami is now battling with the referee. こっちか。どれだこれか Oh, this one, physical research now, 2022. So then this one crystal structure, then we put the muon multi-moment, just like as a model first, then we compute, we calculate this multi-moment in the quantum viewpoint. Then this one is the quality and muon spin relaxation. Then we do the experiment and see the internal field. Then next one, we calculate the inside, the electric state of the lanthanum 2 kappa 4. Lanthanum 2 kappa 4 is a mother material of the high DC, very well known, very well studied, more than the 30 years, but still mystery. Then, for instance, this kind of calculation has recently been done by some researchers only. So then, just like maybe this one is second realistic calculation result of the multi-moment in lanthanum 2 kappa 4, very realistic. Then they will calculate the quantum effect of the position of muon, then analyzed the distribution of the multi-moment, and also muon. Muon is a light particle that should have the 0-point vibration motion inside the real materials. Then we can calculate also calculate the such kind of the spatial distribution by the 0-point vibration motion. I think you know about the 0-point vibration motion. That is the restriction of the quantum theory. We cannot stop the particle in as a one position. If you want to try to put the one particle in one position, that will distribute automatically. That is the quantum physics. So then we found in the end this kind of calculation result. We are required to put on. Then we discuss in the end Coulomb potential between the kappa, at the kappa side. The Coulomb potential. Coulomb potential, we say you have based on the Hubbard model. It's very difficult to discuss. Everybody, especially theoretician, always said the fixed number for the Coulomb potential, but we tuned. Maybe this one is the first study to tune the Coulomb potential and find out the realistic values. So this one is a computation, the efforts for me. So then if you're interested in one of two, like a Mirsar or computations, please contact me. At this moment, one lady is now working on the DFT side. She is from Thailand. And there is a very large DFT group in Thailand. Then from Kasesat, then she's now studying the computations. So these are my background and Riken institutes. So then now, what I want to talk shortly is new project. Sorry, this is just written in Japanese. So because this one is just like how to apply the grant to, how can I say, speed up the communications between the Indonesian groups and also Japanese groups. So there is a very big grant, then to accelerate the international communications. So my scheme is the Japan. There are many special equipments and special researchers to work on the material sciences. Okay, and also what is the specialty of Indonesia, Malaysia, Thailand is you have your own, how can I say, materials. You know, materials means like vegetables and also like ions. Iron is very famous in Indonesia. You have many places to produce the iron oxides or iron phosphide something. Then by using those kind of natural products, so then we can apply the natural products for the mother material, original materials for battery systems. So keyword the battery and also like energy materials, but produced by natural resources in Indonesia. And one group in ETS, Process Darminto, is now trying to produce the carbon materials from the coconut shell. Because coconut shell wastable, you know, we can throw away. Then we can have that free of charge. Then if burned and synthesized, we can have the graphenes. That is his study at this moment. The graphene is very important for the battery, the anodes. cathodes, and also iron sand, and iron phosphides that can be produced around ETS Surabaya. And iron phosphide is also important for batteries for anode. So how to make that kind of battery materials from natural products, that is a very important point for the Indonesian industrial field. But unfortunately, at this moment, there are no such kind of studies, especially in universities. Of course, Japanese companies, they are working on much battery systems, and by using high tech, they are producing much more higher quality batteries, but in Japan. That means that Indonesia has to buy such kind of expensive batteries from Japan. But if you can produce not high quality, but better quality batteries within Indonesia, within the country, by using natural product, that is cheaper. That is also cheaper. Then if you can develop the quality, that is the best. Then Japanese company can buy those kind of batteries from Indonesia and import to Japan. Of course, high quality battery sometimes is necessary, of course. Okay. For instance, cars, there must be the high quality batteries, definitely necessary for cars. But for instance, not only for cars, but also for other purposes, the natural batteries, like batteries for housing, something. Sometimes we don't need a high quality battery, but better quality battery is much nicer if that is cheap. So that is the how can I say, the theme to apply the grant. In the past, such kind of how can I say, collaborations between Japan and Asian countries has been accepted, but that was also finished. But that is for the designing by using computation techniques. Then I'm not suggesting to do the realistic by using realistic materials. Then what is the plan is if you can work, or some of you can work on the a product that produce some materials like graphene, anything is fine. Bioresources, something by using the natural products, but maybe not so easy to analyze the electric style material itself. Then the researchers will come here and to discuss probably with some of you. Then we can provide our facilities to analyze, to study your materials. That is the plan. So in order to accelerate this kind of communications, I set up, I will apply again this year. Then if I can get that grant, I can invite many researchers, like 20, 30 researchers from Japan to here, to have conferences, to have meetings, to discuss together, then how to find out. But not only for batteries, if not only 100% not necessary, of course, but 50% battery materials, that's also fine. The rest of 50%, maybe we can contribute to your researchers. My small grant by using the Sakura Science is a part of them. For instance, next week, they are interested in the development of computing science in Sulawesi. Then my old student, Ilwan, he'd like to show that what is the real and first-class computational system in Japan to young students, to encourage young students. The next one, this is one is to use my squid systems. I have 2 squids. It's not new, but still working well. And by developing the sample setup system, the quality and sensitivity of my machine is better than the latest machine. Latest quantum design, they have MPMS3. So that one is very expensive, very expensive. Maybe in Japan, that was 10 billion rupias. 10 billion rupias. So my one is less than half, but I've got free of charge from my collaborator. Very old, but still working well. And then developing the sample setup system, the sensitivity is not better than the MPMS3. Wonderfully better. The 10 to minus 8 or 10 to minus 7 EMU per EMU per mole, something like that. So then by using those machines, the RISI would like to study the superconducting system. Then we've got a grant, Sakura Science Program grant. And he's going to stay in November, December or November, October or and November for 3 weeks. Then we register 10 students and plus 3 staffs. So now I'm now applying the visa now. And that can be done very soon. Then they will fly from Indonesia to Japan and stay in Riken for 3 weeks by using and use our squid machines to study their materials. Then my team member, my friends, have MUSR, NMR, neutron, radiation, synchrotron radiation, and also computation and sample synthesis techniques. Almost all the techniques we will cover by using my grant. So then if this grant is successful, we can bring many people to here. In order to accelerate, or in order to make this opportunity much more valuable, what I can suggest is to think about, not to all, just only a couple of people, to think about like a study on the materials which are produced by natural products. Or bioresources is also fine. Bioscience is also fine. And also carbons, the batteries, and the sodiums. At this moment, the sodium is a quite good target for the batteries. So how you can provide the sodium, the oxides, from natural products to synthesize materials. And also that theme is also good in Indonesia as well. Then not so bad, not so difficult to get grant if you work on the battery, the materials. At this moment, battery is very, very important for Indonesia, not only for Indonesia, but also for all the world. Japan is the same. Then I'd like to ask you to think about, then the collaboration. You can provide samples, then we can provide the systems. Now this moment, we are now, can see the university logos here. We are now registering these kind of universities in Thailand, Malaysia, and Indonesia, and also Japan. So maybe I will modify a little bit. So then if you're interested in, I'd like to restart the UI again into the this grant application. So this is the image. For instance, from coconut, and I forgot the name of this. Very not famous, they're very natural in Indonesia. So that we can provide the cathode, like a graphene or something, from coconut shell and I forgot the name, especially Indonesian. In the pond or in the lake. Something like this. So from this kind of the natural products, we can provide the graphene. But graphene, the quality is important. How to qualify the graphene, which is coming from the natural products. That is a key technique as a material science. Then we can characterize your samples by using our techniques. And so this one is a phosphide, the phosphide oxide. And this one is this iron sand. They produced in Indonesia. Then this one is anode side. Then it used to be lithium, but now we can do the sodium. Then how is the sodium, the oxide, how you can provide? That is the one question. Then if possible, I want to have this kind of, again, the meetings in Bali or somewhere after next year, if I can get a grant. Then to discuss how we can work together with the Japanese researchers. This time, I invited around here, maybe Japanese researchers here. Then at least I can invite more than 10 people. So then there, as a prayer, like a first step, I invite maybe 10 people to the next Bali conference in November. So if Bali, they said, Lucy said, maybe in Nusa Dua, very expensive price. Nusa Dua, not Sanur, Nusa Dua. Rua. Oh, the Nusa Dua is not decreasing. Oh, I see. Anyway, good. Better than Sanur. but this is they will choose a cheaper hotel in the but that is still fine. As long as that valid, we can relax. Then I will invite maybe 10 to 15 the researchers from the many fields like a neutron, NMR, as much as possible, from young to the elder persons. And also I will send my IPS student, my students, to Bali conference because I've got a special grant, especially to send, especially students only. Then maybe I will send Anita Utami. they are from UI. So then maybe I will ask them to have the oral presentation in front of you, especially Utami's presentation should be very nice. So also they selected in the Paris conference, they're very nice. And these days, her study is very well focused by other groups. Many questions are coming in. And also maybe number 1, number 2 professor in the world for frustration. He's very interested in the Utami's, the presentation. Then last year, she presented in other conference by Zoom. After that, she discussed with the professor, maybe 15, 10 minutes, 15, 20 minutes by using the chat. But this year in Paris also same. After the presentation, the professor came to Utami and discussed. So maybe her study is very focused and very interesting. So maybe I will ask Risiku to give the oral presentation for Utami-san. So this kind of this one is a very big grant. They are simply now, this one last year's one, already 19 pages. Now this year is also, but 19 pages except for titles and grant and team members. In total, this will be like 30 pages. So then I'd like to ask you to think about this opportunity. If you start to discuss with other people who are working on the bioscience, bioresources, or Darmin-san or Risiku, maybe you could have like an image, and maybe no need to concentrate too much, just as like a part-time job. I'd like to ask you to start to think about. That is my suggestion, new suggestion for all of you. At this moment, there is no such kind of activity in UI, as long as I understand. Only Ristik and Darmin-san, they are working on this. Hopefully, the other people, they can start to work together with us. So that one is this one is my talk. Then sorry about this. Budi-san asked me to have a seminar just before I left from Narita. Then I was very surprised. Utami-san sent me a message. Watanabe-san, you have a poster here. Then you should have a seminar here. Then I said, I didn't know about this. Then it takes time, and also airport, it took time again. Visa on arrival, very slow process. Then everything was, luckily there is no congestion from the airport to the hotel. Within an hour, I could come. That was a lucky point. But now, then I couldn't prepare anything. Then just this one, all the slides. Sorry about this. But hopefully you can understand my background and also my suggestion to encourage and accelerate the collaborations. And also, if you have PhD students who are interested in the computation or my material science study, just please suggest. Or if your students are super rich, they can come to Japan by using their money, of course. I don't mind. For instance, Thailand people, I've got Thailand people a couple of years ago. He's got a scholarship from Thailand government and stayed with us 10 months. And this year, I had the one Chinese student. He had 6 months scholarship. He has 6 months scholarship and stayed with us. Both are working on the computation side. So then if you're interested in, just please contact me. The application will be open soon, maybe after the summer, immediately open. Then we have to apply. Then, of course, there is a competition with other people. But if you're interested in, please contact me. So last year, I got one student from Unpad. And Anita-san, she waited for 2 years due to some the COVID and her personal reasons. Then, but she's now seems to be enjoying staying in Riken. And she came back from Vancouver last week. Maybe she's being suffered by a jet lag, strong jet lag. Maybe okay, maybe okay. Okay, thank you very much. So that is the end.
Thank you, Professor Watanabe, for nice talk for us here. And now I would like to invite to you, if you have any question or anything you want to ask, please, you can speak up here. Thank you. Who wants to? Mungkin dari yang di Zoom? Ada? Bisa, ya. Untuk teman-teman yang di Zoom, silahkan kalau misalnya ada yang ingin bertanya, ya. Kita bisa dibuka itunya, mic-nya. Silahkan. Yeah, I think the main thing that Professor Watanabe mentioned to us is about the possibility of the collaboration in exploring our natural resources, yeah, something like coconuts, yeah, and also eceng gondok, yeah. Eceng gondok, to produce, yeah, by us, and then to give some of the energy material. Ya. Mungkin ini menarik Pak Jati untuk teman-teman kita ya di Fisika UI, karena di Unpad dan di ITS sudah Pak Risti dan Pak Darminto sudah melakukan itu. Ya. Jadi beliau berharap dari kita kalau bisa ada yang bisa memanfaatkan. Okay, is there any question? I want to ask you about the squid facility in Riken. You mentioned that you have 2 machines, isn't it?
Oldest one and medium one.
Oh, okay.
But if the signal is very large, like a superconductor, both doesn't matter.
Okay. I want to ask about the magnetic field.
Both are 7 Tesla.
7 Tesla.
7 Tesla.
7 Tesla. Okay. And how about the temperature?
Up to 330 Kelvin.
To
330 room temperature.
Room temperature. For the high temperature, they cannot work.
Beyond the high room temperature, we have no system.
Okay. Okay. But the low temperature is it possible?
Low temperature 2K.
Okay.
2 Kelvin.
2K.
2 Kelvin. Good enough.
7 Tesla and 2K. Okay. Yes. Yes.
Right. Hello. My name is MJ Prakoso. Well, I am an alumni from Department of Physics, Universitas Indonesia. Well, I wonder what makes MuSR and ESR different. That's number 1. And number 2, can we use MuSR to discover the properties of topological properties in a material? Well, I think that's all for now. Thank you very much.
For instance, MuSR I'm doing, and ESR, you're talking about ESR, possibility to use ESR, okay? I think that Buddhi-san knows about one guy in my laboratory, in my group, the Yugo Oshima. Oshima-san, he moved from the old laboratory to me, to our laboratory, and he's now working with us. So he's a super specialist for ESR. Then Buddhi-san has got one paper in the past with Oshima-san. So then if you're interested in ESR, of course, Oshima-san is a good target. And also, if you're interested in, of course, you can apply the IPA with Oshima-san. Also fine. And also topological system, also not so easy to say, but there are some activities in the world. Some researchers are trying to detect the surface current by using the MUSR, especially at PSI, Switzerland, because the surface physics, we have to use ultra slow muon beams in the PSI. But I used to try, once I tried with my friend, but I failed. So at this moment, by using MUSR, nobody has succeeded to pick up the surface current, especially topological systems. And also other themes for topological systems, the MUSR seems not to be so effective. Rather than MUSR, maybe neutrons and radiation light source could be much more better to discuss, because you need to discuss the band gap around the Fermi energy. That Dirac-like or something. MUSR unfortunately cannot pick up such kind of structure or the band gap around the Fermi surface. Maybe the light source could be better, or Raman something.
Thank you. Well, now I would like to ask about Abrikosov lattice. Is it different from your same old crystal lattice, or is it actually the same but a different kind of form?
Now, Abrikosov lattice is just like a superconducting state. That can be studied by MUSR, but of course we have to be carefully studied, because the difference, the Abrikosov state, it depends on the Cooper pair symmetry. But differences among the Cooper pairing symmetries are not so big. We have to use the MUSR with the high statistics and careful analysis. Dieter has published a paper, one paper in PRB, 2000, maybe this could be a good reference for you. I show you now. 芝子、これか。パウダー。This one, last year, Dieter's one. This one, organic superconductor, and we applied the MUSR, and she also did the DFT, but this one is a little bit not so clear. So then she studied the superconducting state by using MUSR. This curvature reflects the state of Abrikosov distribution, Abrikosov lattice. Then she analyzed this Abrikosov lattice state by using her own new type of function like this, S wave, D wave, S plus D wave, and she named H wave. So because beyond F, SPD, then now sometimes F something, then she named H, hybrid, the H shape. That means the state of the Abrikosov state or Cooper pairing symmetry is different from S, different from D, different from P. Then she named as deformed, they D-like, the symmetry. So then in the end, she completely analyzed and decided the gap symmetry and gap value. So this one is maybe could be one example to your question, to answer to your question. Just see this one. I personally think this one is open access. We said this paper to be in open access in a PRB. Maybe you can download.
Thank you very much.
Is there any question? Pak Jati?
Thank you. Thank you, Professor Watanabe, for a very nice talk. Very informative, very comprehensive. For several pictures from your PPT, looks like your students are happy. And Utami also quite famous in your group. As you know, Utami is a student from graduate program in our department under supervised Professor Budi. Yeah. Okay. Professor Watanabe, if is it possible if I have a sample or somebody has a sample and then want to access your Muon measurement? I just sent to you a sample, or we need to discuss first, or I don't know.
Of course, we need to discuss first how much we can have the data by using MSR. Sometimes that is well known, and sometimes in some sense waste of time. We have to see the material first and what kind of the physics you want to develop by using the MSR and your samples. That should be discussed first. Otherwise, even though you write down a proposal, maybe not accepted. Not so easy because the MSR is very expensive. The system. Every day we have to use how much? 60万、100万、100万だから1 million, 10 million, 100 million rupees per day. Operation cost. 100 million rupees. 1 million yens per day. The electricity and only electricity and also helium cost something, excluding the labor cost. If you include labor cost, maybe it will be nearly double. Very expensive. So then we have to have a stronger, severe screening system. Sometimes competition is too hard. Then better to discuss first. Maybe call for proposal will be open in October, I guess. Maybe yes. So better to discuss first. So if possible, if you like, better to measure the squid first or X-ray squid first to make the background data stronger. Then I'm going to cool down the squid at the end of August. 2 squids will be cooled down and to prepare the resequence, the program. And after that, I will warm up one old one and we continue to use the medium class one, maybe till the next year. So if you like, you send samples, we can measure, no problem. If you say to Utami-san, to measure this, she can say no. No problem. And also Anita-san, she's going to learn how to use a squid very soon. So maybe she can operate well, but now she has to learn about more techniques very soon. So maybe you have people work for you, no problem. And also I can manage everything. And also I can operate a squid by myself, of course, no problem.
Okay, thank you, Professor.
Okay. Is there any question? Pak Jul? Pak Cahaya? Pak Michael? Nah, ini Pak Michael.
Thank you, Prof. Watanabe. My question is about, you mentioned about collaboration about this energy material, right? Especially for battery material. I remember last time you offer us to propose that things. Actually, there's plenty of opportunity in Indonesia, but we also need the direction from you in respect to the technique that we will use later, right? Example is last time we talk about, let's say, when we use graphene or like in plastic, also got problem in here that we can use to make something like a layer to block the ion inside the battery, like a metal organic framework. I think Unpad already started that thing. What do you think? I mean,
the topic that we should, because we are all physics, we are not chemists. That's why quite troublesome to, we have some problem with synthesize, Prof. So do you have any idea how we start this thing first before we
Yes, for instance, in the world, I think you remember this guy, Alan Drew.
Yeah.
Alan Drew is a physicist, of course. He is a physicist. He doesn't know how to synthesize any materials, but he's collaborating with the chemistry people in the Queen Mary and also London College. And also another people in Oxford, they are pure physicists. Steve Blundell and so Darlan, Tom Lancaster, they are completely pure physicists, but upper class, super high class physicists. They don't know how to synthesize chemistry things. Then what they are doing is collaborating with the chemistry department.
Okay.
So then the important point is not to only within the physics, but also better to talk with the chemistry, the groups within the UE. Then you can expand your collaborations with, I can say, inside collaborations that are also important for you. For instance, in RIKEN, we are also recommended to work with other researchers within RIKEN, crossing the fields. Like then I'm now talking with AI guys, AI people. Sometimes I talk with the chemistry people, and also I'm not talking with biology people. That's like a DNA, for my DNA project. And also computation people. So that is important. Then you can learn many things that even though you cannot synthesize by yourself, you can, how can I say, you can tell your ideas to the chemistry people. Then chemistry people can synthesize for you. That is very important. For instance, I don't know about the computation technique, but my student, my collaborators can do the computations. So that is also important. I don't know about the AI, but AI people can suggest something. That is my belief. I definitely believe better not to be within the team, but also better to talk with other team members. For instance, the domestic, international, the university, and crossing universities. That is the important point these days. That is my belief. Maybe you can do. And I have a question to you. Well, what is the affiliation now? You are always moving. I don't know who you are.
Yeah, I still with now. My affiliation is in Indonesia Defense University.
Here.
And also here with
also
Prof. Budi.
I
Yeah.
see.
And one more thing, Prof. I have collaboration with industry, GS UASA in the Sekarang. Is it possible to? I mean, is it? Can you elaborate? Can we?
Of course. I recommend you to discuss with the company people.
Oh, okay.
The problem is the patent.
Patent, yeah. All right.
Patent problems sometimes they are very strong, but better to discuss with the company people.
Okay.
For instance, in Japan, there used to be research groups in Toyota company, but he retired from Toyota, then moved to the JAA. But I personally think they can discuss with Toyota Group, but due to patent problems, we cannot have any latest materials from the company. That is a problem.
Okay.
But I think maybe the USA is much more smaller than Toyota. Maybe they should be very flexible rather than Toyota. Toyota has a very, very strong and severe restriction on patent things. They don't show any decent results. So that is a problem. So then even though we do something, that is not the latest, the research, already delayed. So not so interested in for especially industrial companies. So that if USA can provide you some new material or something, also interesting. Then we are research National Institute, the Japanese National Institute, we know about how to keep the patent. So then maybe USA can work with RIKEN and with you, of course. Better to discuss with company people as much as possible. Then you can have more ideas.
May we consult you about this later on? I mean, for future, for now, maybe we try to gather ourselves in the
Yeah,
university
for instance,
first.
maybe USA has maybe new possible materials for the next generation, I guess.
I'm not so familiar with that.
So then if you can provide the natural resources for battery materials from Indonesia, from your side, maybe USA is very willing to use, I guess, much cheaper.
Oh yeah, yeah. Thank
And
you.
huge amount of coconut shells you can have.
Yes.
No problem.
Yeah. Okay, thank you. I think that's all. Thank you very much.
Baik, ada lagi yang di Zoom? Ada yang ingin bertanya barangkali? Kalau ada yang mau bertanya silakan buka mic-nya. Ya, jadi artinya Prof. Watanabe ini hampir setiap tahun berusaha untuk mencari calon mahasiswa S3 yang dalam bentuk IPA program. Is this still available for IPA program? IPA. Yes. Would you like to explain about the IPA in short?
IPA system, IPA program is to encourage PhD people. So then only for PhD at this moment, but will be open for master course student. But at this moment, I reckon it is still discussing how to open. Maybe not yet. But IPA program, the people, the master in the student in the last year the master course, they can apply. So important point is to be in the doctor course when they join to reckon. Usually we start from 1st of April, that's the first round. Second round is 1st of October. That means if students it belongs to the PhD course from 1st of April or 1st of October, they can apply the IPA. So then the IPA, full-time IPA is 3 years. Then the condition is very well. So you can have salary, which is good enough to survive in the Riken area. And also students can stay in the Riken dormitory for 3 years, full-time. Then they buy free of charge. So quite good condition. So then the first IPA student was risky for me. They risky in the first, then followed by many Indonesian students. But of course, not only for first year, but also second year, third year, you can join. So full time means beyond more than 1 year, but less than 3 years. That means 2 years also good. One Chinese student graduated in 2 years. Then PhD, the award will be awarded from UI. That means you don't lose any UI status. Just like a scholarship like. Then, but you can use the Riken's grant, Riken's money, and Riken system. But from next year, I don't know how much grant I have next year. Maybe poor, maybe rich, I don't know. But that is my duty to get money, of course. So then the students, can enjoy with us. Then I have some furnaces to synthesize oxides and X-ray diffraction, diffractometer, and squid. And I have collaborators who can provide many things. And also Oshima-san can provide the ESR system. And also, if you like, I can provide NMR system. I have also NMR system with me. And I have 12 Tesla magnet, but I didn't use yet. I bought a long time ago, but due to the heavy operations, I didn't use a 12 Tesla magnet. But if you like, you can use a 12 Tesla magnet. So those kind of opportunities will be open for IPS. And also students can work with my collaborators. For instance, Utami is now in Sendai. They're working with my collaborator on the FZ, the single crystal, the synthesis.
Okay, thank you for the information. Okay, jadi informasi tentang IPA program yang
Sorry, one more again.
Yes.
IPA program is open twice per year.
Mm.
The second call is coming soon. But I have to give the interviews first. Then I have to judge whether your English performance is good or not. And also basic knowledge is good or not. Especially English performance is very important to discuss many things. That is important.
Oke. Jadi IPA itu semacam scholarship, ya. Artinya status kemahasiswaan di UI tidak hilang. Ya, jadi artinya justru ini sangat menguntungkan. Ya. Ada 4 orang mahasiswa kami yang sudah menjadi pengguna dari IPA itu. Ya, Redo tadi yang sudah disebutkan, Suci, Utami, sama satu lagi Anita. Hampir setiap tahun beliau nanya saya, ada nggak mahasiswa kamu yang mau ke sini? Ya. Tapi memang bidangnya beliau tadi USR, lalu kemudian computational Muon gitu ya, dan tadi ya seperti superconductivity gitu ya. Nah, itu tema-tema yang memang menjadi bidangnya beliau, karena kalau bukan itu beliau menolak biasanya. Ya, karena biasa orang Jepang kan sangat strict dengan bidangnya beliau. Gitu. Jadi itu sangat menguntungkan sekali ya. Dan biayanya itu scholarship-nya besar. Saya pernah mendapatkan beasiswa dari Jepang gitu ya. Dan dibandingkan dengan ini, ini makmur. I just say that the IPA scholarship is more than the Mombuktago. So.
One more thing for the graduate PhD beyond the PhD system, the Japanese science promotion JSPS, they provide the postdoc jobs for 2 years. The call is open twice per year. Next call will be open from end of August. End of this August. The second call will be open. So if you're interested in, you can apply this. But in this case, you don't need to come to me. If you have good collaborators and professors, you can contact with them and apply. The condition is very nice. Salary per year is 6 million yen.
6 million.
6 million. And the research money is 1 million per year. The condition is very, very good. But of course, competition is too high. Maybe 10% people can pass through, only 10%. Utami applied once, but failed. So also, again, she applied, second applied. If she fails, she will apply again.
Oke, jadi artinya yang sudah S3 pun juga ada kemungkinan peluang untuk postdoc. Ya. Postdoktoral di RIKEN. Ya. Jadi terbuka peluang ya. Kemungkinan bisa dimanfaatkan di sana. So we have a question from the audience in the Zoom. Ya, from bisa di ya Fisika Imam dari Unhan ya, Imam Mukhlis, Pak kenal ya, from Defense University, is it? Ya, okay. Thank you for the marvelous presentation, Professor. I had one question I still not fully understand. What is the physical relationships between USR and density functional theory? I'm sorry I can enable my mic because it got a problem. Yeah. Could you like to answer the question? What is the physical relationship between USR and density functional theory? Thank you, Mr. Imam. Yeah.
What the physical meanings is, better to show my paper, Ramadan paper. This is also the open access. If you're interested in, please download this. Maybe you can understand. Physical meanings is the two connects between experimental result and also computational techniques. So this one is the figure is here, figure 3. This one experimental result of MSR. Then what information we can have from this data is internal field at the muon site. This one is the Fourier spectrum of this muon spin precession. So then here, frequency is say like between around less than 6 megahertz. Then that can be converted into the internal field in Gauss by using the gamma value, those are muon. Then we can discuss how much internal field appeared at the muon side. Internal field is coming from surrounding magnetic moment. Then how to estimate the surrounding magnetic moment, that depends on the DFT. Then we estimate, this is density of the magnetic moment. But we use a μSR, that means we put the muon into the material. The muon can be a magnetic impurity, direct magnetic impurity. How to estimate the effect of the direct magnetic impurity to the distribution of the magnetic moment? That is a key question. Then the Ramadan, they estimated the position of the muons. Then they discuss, estimated the black points are the muon position, muons. Then this muon deforms the distribution of electromagnetic moment near the muon. That means the internal field should be changed by putting a muon in, but muon is a prober of the internal field. That means the muon is probing the internal field, but muon is distributing, modifying the internal field. Such kind of modification has to be calculated by the DFT. That is the DFT's, the technique. Then they tune the parameters. At this time, we tune the parameter of the U, of the Hubbard U. Then if you tune the Hubbard U, the size of magnetic moment is changing. For instance, this one, for instance, magnetic moment is changing by changing the Hubbard U value. Then calculates the distribution of this magnetic moment by DFT, then sum up the dipole field at the muon side. But unfortunately, muon side is also distributed. This one is 0-point vibration motion. Then each point we have to pick up. For instance, each magnetic moment component is calculated as one muon position. Then muon position is also summed up, everything. Then we evaluate the internal field. Then we match. We make matching between experimental result and also computational result. That is the physical meanings between the MSR and also DFT. So this kind of study is very famous and active now in the world. And competition in the world is very strong. The very simple, the programming to estimate the muon position is being released, but it's too simple. Then we cannot discuss this kind of the physics. So in order to discuss the physics, they better to follow up this paper. Then tune the U value. It's not so easy, honestly speaking, because we have no experimental result. Usually computation people decide, U value, the 7 dB, 8 dB something. But we carefully tuned the U value and decided the optimal U value to be nearly 4.8 something. So that value is now well evaluated these days. Used to be 9 eV or something. In the beginning of high-tech story, we discussed U value to be 9 eV, but that was too much. Then reduced year by year. So then now nearly say 5 eV. So this one is second, maybe second exact the example, but first exact example, but second the estimation of the U value on the Lansan 2 kappa 4. That is physical meanings.
Okay, Mr. Imam, can you understand what the explanation of the Professor Watanabe? If you want to write down, yeah, you can write in the chat. And the next, Mr. Fatan Bahti, could you like to open your mic and you speak up directly to Professor? Okay, thank you, Mr. Imam, for your reply. Yeah. And thank you also for your question. Mr. Siapa tadi yang? Yeah, Mr. Fatan Bahti.
Oh, yeah.
Yes,
Yeah.
okay. You can speak up.
Yeah, thank you, Mr. Adam. I would like to ask about the possibility about research about mineral processing in Japan. Is it possible to do it in Japan, or maybe we need do research, another research or something like that? Maybe like that, Mr. Adam. Thank you.
Maybe this kind of the research seems too early for me at this moment. That is why I'm now trying to apply the grant to start to discuss this kind of the energy system, especially you are talking about the mineral processing for energy application. So sorry, I don't understand what the meanings of mineral processing for energy application. I don't know about the your targets, but maybe if you work on the chemical synthesis, the chemical synthesis of some materials, I'm sorry, it's not my field. I said to you already, I'm not the chemistry people. I cannot synthesize.
Okay.
If you synthesize, we can measure, we can characterize. So that is
the, maybe I will tell a little bit about my topic. Is like I do extractive mineral is like from laterite, like doing to take the nickel for battery, so like that. And not just for take the nickel, but I'm doing like for synthesis also for nickel nanoparticle like that.
Sorry, still I cannot understand your target material.
I mean, sorry, for the
Mr.
another
Patton,
voice.
would you like to speak
I mean,
loudly so we can?
I mean, sorry for the another voice in here. I mean my topic is about the extractive of laterite for taking the nickel, and then the nickel application is for battery. So my topic is not just the taking nickel, but also I'm doing synthesis of nickel from laterite ore like that, bro. Is it possible if I do research in Japan like that? Is it clear?
As I already talked, the synthesis is not my field. My synthesis is like the oxides. So then I cannot teach how to synthesize chemically. That is a problem. So then, as I informed, I told you already, you synthesize, we can characterize. That is my standing style. So then, just to synthesize, as like a PhD study, maybe not so good. Maybe better to choose a different professor. Or who is the supervisor to him?
Okay. Maybe if I mean, it's like if we have a possibility to do research in there, maybe I will like make some research also in there if there is some possibility like that, Prof. Thank you. Maybe I will give back to Mr. Adam. Thank you, Prof.
I recommend you to discuss with Professor Budi. He knows about the physics, so that if he can understand what you want to do, there could be a possibility. But please discuss with him first, because still I don't understand your target materials, and I cannot judge. I cannot say anything.
Maybe just like characterization of after a synthesis of nickel, maybe like that to do in. I mean, in the battery, if like is it good or no, like that maybe in your lab.
Pak
Ya.
Pak Pahan bisa dalam bahasa Indonesia aja coba disampaikan.
Maksud saya mungkin kan tadi karakterisasi ya, Pak. Jadi
Karakterisasi.
saya berbeda kan sintesis ya. Dia sintesis berbeda tidak di labnya kan. Ya udah mungkin saya cuma tanya apakah ada kesempatan di sana di Jepang. Kalau memang selain dengan Prof Tanabe ya berarti kita ya cari ke Prof lain, mungkin nanti dari Prof bisa gabungkan ke Prof lainnya mungkin nanti ke depan itu Pak. Mungkin saya diskusikan dengan Prof Aswar juga gitu Pak.
Oke. Oke, nanti mungkin kalau misalnya sudah clear nanti bisa disampaikan ke saya, nanti saya coba tanya ke beliau ya.
Oke, siap, Pak.
Peluang-peluangnya begitu ya.
Iya Pak, maksud saya peluang itu Pak untuk bisa riset di Jepang seperti itu.
Iya, iya. Oke.
Terima kasih Pak.
Ya, sama-sama. Oke, terima kasih pada Mas Fathan yang telah menanyakan tentang kemungkinan untuk melakukan riset di Jepang ya. Artinya tentunya nanti perlu dibicarakan terlebih dahulu detail dari apa yang dilakukan dan kesesuaian kalau misalnya dengan Prof. Watanabe disesuaikan dengan fasilitas yang ada di sana ya, dan juga apa saja yang bisa dilakukan di sana gitu ya. Kalau tidak mungkin nanti kita bisa mencari tempat yang lain gitu. Ya. Oke, baik, terima kasih. Is there any question from others audience? Who is? Pak Cahaya? Ya. Baik, I think there is no question again. Yeah. Let's give applause to Professor Isa Watanabe. Yeah, for nice talk today. Yeah, although he didn't prepare the presentation, but since this is his activity, yeah, in Rikeng, so he can give us any information. Yeah, we have some of the advantage from this discussion. First, we know the facility in the Rikeng that we can use. Ya, Pak Jati ya. Tadi seperti misalnya MPMS ya. Artinya pengukuran dengan menggunakan squid di mana batas suhunya adalah dari 2 Kelvin sampai dengan 300 Kelvin. Ya, sampai suhu ruang. Di atas suhu ruang tidak ada fasilitas yang ada di sana. Medan magnetnya sampai dengan 7 Tesla. Ya. Dan juga is also ESR, yes, ya, bersama osimasang, ya, itu juga suhunya sampai 300 Kelvin juga. Tapi dia hanya punya X-band, ya. Jadi hanya X-band saja, ya. Tapi variasi suhu. Ya. Tidak ada variasi untuk Q-band gitu ya, kemudian K-band gitu dan sebagainya. Dia hanya X-band saja, tapi untuk bisa kita variasikan suhunya ke suhu rendah, tapi tidak bisa ke suhu tinggi. Ya. Kemudian tadi ada informasi terkait dengan peluang untuk kerjasama dengan memanfaatkan ya sumber daya alam Indonesia, kelapa, eceng gondok, ya, yang bisa dimanfaatkan untuk ya ke baterai tadi ya, jadi energi material. Ya. Jadi itu bisa nanti teman-teman yang di Fisika UI yang ingin ataupun juga mungkin selain di Fisika UI di kimia gitu ya, di MIPA ini bisa ya. Nanti kita bisa diskusikan di Fisika ya, nanti kita akan sampaikan ke Prof. Watanabe ya. Dan beliau sangat berharap itu kenapa? Karena di Unpad sudah dimulai dan juga di ITS ya. Jadi artinya mudah-mudahan kita juga bisa berpartisipasi dan dia berharap juga dari UI bisa bergabung di situ ya. Dulu kita memperkenalkan ke beliau ya lewat Pak Michael ya, Bu Evi ya. Alhamdulillah sekarang sudah running dengan Prof. Alan dulu dari Queen Mary University di UK. Lalu kemudian informasi tentang peluang-peluang beasiswa dan postdoc. Ya. Jadi IPA program itu untuk PhD, doctoral degree 3 tahun, dan juga untuk yang mau menyelesaikan master degree ya di tahun kedua. Namun tentunya bidangnya harus sesuai dengan bidang beliau, gitu ya. Ya, artinya
Budi-san.
Ya.
If you talk about IPA program,
Yeah.
Utami-san is on.
Oh, ya.
Utami-san.
Utami-san.
Can you comment about the IPA, the experience of the IPA? Indonesian language is fine. Can you share the screen?
No.
No.
Okay. I'm still in the birthday. Oh,
Sorry, network is not so good.
yeah, connection here.
Yeah, become better.
Yeah, it's better.
Hello, Utami-san.
Yeah.
Would you like to close your mic? Yeah. Closer to making yes.
Okay. Can you hear me?
Yes, okay.
Yeah, maybe I just want to talk about IPA status. So
Indonesian language is fine.
I've got the IPA.
You can use Indonesian
Okay.
language.
Ya, jadi saya dapat kesempatan 3 tahun sebagai IPA student, terus benefitnya banyak. Kita bisa kolaborasi dengan orang-orang yang ada di sini gitu. Terus tapi ya itu tadi sesuai sama dengan yang Pak Budi sampaikan, kalau topik risetnya mengikuti topik riset beliau gitu, tidak bisa di luar itu gitu, karena kalau di luar itu mungkin juga beliau tidak punya capacity untuk supervise kita gitu. Nah, terus apa lagi Pak? Oh, kalau scholarship-nya sebenarnya bentuk scholarship-nya itu adalah pemberian biaya hidup di Jepang selama 3 tahun, which is good enough untuk bayar SPP dan untuk hidup di Jepang. Itu sih yang saya alami. Jadi ya jangan berpikir hidup di Jepangnya itu hidup di Jepang berfoya-foya, tapi hidup di Jepangnya juga prihatin. Gitu aja sih Pak. Apalagi Pak? Terus ya nanti setelah lulus kesempatan untuk kolaborasi juga masih terbuka biasanya, as long as we keep the good relationship gitu. That's all. Finish, Watanabe-san.
ありがとうございます。
はい。
サンプル頑張って。
はい。あとは、ワンさんとエカルディメグラ、I will do it. エカルディメグラ。
頑張ってください。
はい。
はい、失礼します。どうもありがとう。すいません、急に。Sorry for disturbing your time. Sorry about this.
Ya, baik ya, jadi banyak sekali benefit yang bisa kita dapatkan, ya informasi-informasi yang tadi disampaikan baik oleh Prof. Risa Watanabe maupun juga oleh Utami, ya, yang menjadi artinya pelaku ya, artinya beliau pernah mendapatkan itu, merasakan itu, dan tadi menyampaikan ya banyak sekali benefit yang didapatkan ya, selain artinya financial support ya, juga kolaborasi, bisa kenal dengan para profesor-profesor yang terkemuka di dunia, bisa diskusi gitu ya, dikasih masukan dan lain sebagainya sehingga bisa memperkaya dan lain sebagainya. Tadi kan Prof. Watanabe mengatakan ketika dia presentasi di Perancis, di Paris itu ada profesor-profesor yang terkemuka kemudian mendatangi beliau diskusi segala macam, itu kan luar biasa ya. Artinya karena tertarik dengan tema risetnya gitu ya. Jadi ini terbuka ya peluang ya siapa saja gitu ya, artinya tapi tadi ya poin utamanya adalah kalau dengan beliau ya pasti temanya harus sama dengan tema yang beliau tawarkan gitu ya. Baik, mungkin itu sebagai kesimpulan utamanya ya dari Pak Jati. Mungkin ada closing remark yang disampaikan.
Baik. First of all, of course, thank you very much for very nice sharing, very nice talk from Professor Watanabe. Thank you, and maybe next year, you can come to here again. And one more thing, maybe Professor Budi, we need to expand our double degree MOU. Maybe next time from chemistry or biology, we can do it. And for the student, please grab this opportunity. Anything, yeah, you can do it, and it is so possible for all of you. Thank you, Professor, again, and keep healthy, keep safe for your trip. Wassalamualaikum warahmatullahi wabarakatuh.